We're very excited to have Lillian Ratliff from the University of Washington. Lily works on a bunch of like really exciting problems on like learning games, differential games, control theories, and so forth. And today she'll be talking to us about beyond open loop algorithm design. Thanks so much, Lily, and the floor is yours.
All right, thanks, Georgios. Yeah, so I want to talk a little bit. First of all, this is the first time I'm giving a talk in person in like 2.5 years, so I apologize if it's a little awkward. I might find myself, because normally you're like staring at your computer. So, yeah, so if you have questions and I don't notice, just yell out. Yeah, so I want to talk about some of the work that we have going on in my group on thinking about how to close the loop in machine learning. And so in particular, focus on learning from decision-dependent data. And that's suggested sort of by the name of the workshop. We're often thinking about data that's generated by strategic data sources. So we'll start first with sort of the traditional perspective. So if you're thinking about designing a prediction or classification algorithm, or maybe more generally, some decision-making algorithm, sort of the typical way that this is done is that we assume that we have some training data, let's say, that's representative of the environment or the problem that we're going to try to learn about, and then we design our algorithm and we deploy it in the real world. And so we sort of kind of believe that the training data is not going to really depend on the decision of the algorithm. So it's sort of both representative of the past and the future. So what I'll argue is that in a lot of modern systems, this kind of perspective needs to be revised or doesn't really work, leads to unintended consequences. And I'll give some examples here in a minute. But this is sort of spurred on by the fact that we now have, human decision makers that have edge devices and they're able to react in real time, like, for example, to decisions that are being made, whether that's in the context of any one of these applications shown here or various others. So let me give some examples of how things can fail if you stick with this sort of open loop point of view. So we'll start with an example of failures that result from traditionally designing these algorithms without thinking about the fact that the algorithm might change the underlying data distribution. So this is an example of feedback reinforced bias. So not just bias in the data, but also institutional bias related to predictive policing. So there's many companies that provide these predictive policing algorithms. One is this company Predpol. And so this is a study that was reported in this Royal Statistical Society in 2016. And basically what you're seeing here on your left-hand side, I guess, is on the top, this is drug arrest in 2010 in the East Bay area. So this is, we're up here in Berkeley, and this is like the Oakland area. And you can see kind of in downtown Oakland, there's a concentrated spot of drug arrest. And then sort of there's some along this corridor into Fremont. And then in the bottom, you're seeing estimated drug use from a 2011 national survey. And the red is the actual drug use or whatever. And like it's widespread, so it's not concentrated in particular in those areas. Nonetheless, when you use Predpol to predict day-ahead hotspots where this gives suggestions to police of where they can go to sort of look for, do their patrol to look for illicit drug use, it keeps predicting in the same downtown area that isn't really representative of where drug use is. Moreover, at least in 2010, demographics may have changed. This is an area that has a larger percentage of persons of color living in that vicinity. And if you look over here on the right, you can kind of see basically police targeting for illicit drug use by race is concentrated in the persons of color community, while actual estimated drug use by race tells an opposite story. And so that was 2016. Now we're in 2022, and last year, at the very end of last year, there was a leak of data from an unsecured Predpol server that these authors who posted this on Gizmodo basically showed that the problem is widespread and continuing to exist. So these are all, the red locations are using Predpol, and the black locations use some other predictive policing algorithm. So Predpol has a new name, by the way, it's called Geolytica now. And you can see basically, the result of this actual data is showing that, again, it's targeting communities of color, and they also have some plots showing it targeting lower income communities as well. So we recognize there's a problem 5 years ago, and we still haven't really done anything to fix it. Second sort of set of problems that are rising in the space is that oftentimes these algorithms are being trained without considering that the data is generated by human users. So that, of course, is one of the motivations, I guess, of this workshop. And so as another example, this is, in 2019, it was reported that Uber and Lyft drivers were colluding together to cause a trigger in surge pricing. So basically at locations like airports where they have these, areas where drivers can, they congregate before they pick passengers up. All of these drivers would get together and say, okay, I'm gonna turn my phone off. So they would all turn their phone off. They cause a dip in supply. This triggers the surge mechanism to kick in. And then they turn their phones on and capitalize on that. And the problem is this leads to negative externalities because the cost gets offloaded onto the passenger side of the market. So the design of these algorithms wasn't really thinking about, for doing, say, surge pricing, for example, or predicting demand that leads to a decision about surge pricing. They're not really thinking about these sort of unintended behaviors. And it's difficult because at these locations like airports, oftentimes this kind of behavior is hard to detect because there's already volatility in the demand and supply. Okay, so in both of these examples, we have the situation where we're sort of ignoring the feedback loop in the design of the algorithm. And so we want to start moving towards a set of algorithms that can account for this kind of behavior. So over here to sort of set up the problem space, over here on your left, we're seeing sort of this open loop problem. So we want to solve some expected, let's say, loss minimization problem or risk minimization problem. You can also do this in the context of empirical risk minimization, but I'll just talk about the expected loss case. And we want to move towards considering a decision-dependent distribution. So this looks like a simple change, but really it's not. And the challenge is that this distribution is typically a priori unknown. And the reason is that it's generated, for example, by strategic users whose preferences aren't known a priori. And so this really is representative of some information asymmetries between this decision-dependent learner who's trying to solve this problem and the environment where you have this sort of reaction to the decision. So we'll just come back. I'm going to keep coming back to this rideshare example because it's simple and kind of easy to communicate about. And I have some simulations at the end to illustrate some interesting directions for future research. So if you think about this problem of, say, predicting demand based on surge and let's say supply. So let's say you're one of these platforms and you want to take a bunch of supply data and maybe some other features and learn a prediction algorithm for demand. And then you might use this for various things. One thing you might use it for is to create this heat map, which both Uber and Lyft do, that presents information to drivers so they can then react in some way. So now you have your supply, so the drivers sort of reacting to this information that's shown on the heat map. And that kind of behavior can either be strategic behavior, so they're just planning their day, like where am I going to go to maximize my individual revenue, or it could be adversarial, like this collusion example. And so the work that we're doing in my group, and several others, of course, are working in this space as well, we've been thinking about both these problems of adversarial behavior as well as strategically generated data, but also thinking about situations where you have dynamics. So for example, in many behavioral models, in particular, if we're talking about humans, it takes time for them to react to announced mechanisms. So this is pretty typical in, say, prospect theory, in various other behavioral models where humans compare to reference points or they have some history. So we want to account for that sort of delay. So we have a little bit of work in that space. And then we also care about this setting where we have competition. So of course, rideshare is a good example of that. You have, say, multiple platforms that are engaging with the same population of drivers and the same population of riders. And so across all of these kind of areas, the sort of key insight is that we can sort of revisit these learning and decision-making problems using game theoretic abstractions. And so for the rest of the talk, I'll just focus on this one particular area. So thinking about what happens when you have competition between decision-dependent learners. Okay, so I'll just motivate this again with a few other examples beyond the rideshare case. So in many real-world settings, you have algorithms that are interacting. So you can think about, for instance, these mapping applications. So it might be Waze, Google, Apple Maps. They're all giving routing suggestions to different users who are then executing them in the same physical environment. And then each of these routing applications in turn is observing that behavior and making decisions. So there's interaction between the decisions of the different mapping applications and how it impacts the decisions of the users. Similarly, in whether we're talking about university admissions or loan procurement, you might have multiple institutions that have different desiderata. And then you have applicants that are trying to get positively classified by one or more of these institutions. And so they might adjust their sort of application in response to the desiderata of these different institutions. So I want to kind of, before getting into the details of things, I want to just give a little bit of history on this kind of problem space. And so in the open loop setting, we're talking about, say, traditional risk minimization in machine learning. And so then we can start to think a little bit about this closed loop setting where we have this decision dependence. And so this problem, it has its sort of roots in stochastic programming and control. I mean, this looks sort of naturally like either a static reinforcement learning problem or a control problem. And so there's a nice review paper from 2018 covering work going back to the 80s. And the predominant focus here was problems in operations research related to resource allocation. And so for the most part, the work doesn't really think about strategic behavior or the fact that this distribution is somehow unknown and a result of strategic behavior. On the other hand, in the machine learning and optimization community, very recently, there's been several different lines of work. So the first, I would say, started with thinking about strategic classification. There's various formulations for strategic classification. There are several focusing on the optimization point of view that are relevant to what I'll talk about today. And sort of a blanket problem for that is what's called performative prediction. And so there's several lines of work on that, mostly coming out of Berkeley. And so that's already a hard problem. And so just to reiterate why this is a hard problem, if you think about even optimizing this sort of closed loop learning problem, if you will, we can start with first order conditions. And you can see there's this, if we break up the gradient, we have this explicit partial gradient. And this guy can be computed pretty easily with samples. So all we're doing is taking the gradient of our loss function with respect to the x dependence in the loss, so explicit dependence in the loss, and not yet with respect to the decision dependence. So fairly easy to compute without knowledge of this data distribution. On the other hand, if we look at the second term here, this is an implicit, what I'll call implicit partial gradient. And so it's the gradient of this expected loss, given that we have this decision dependent data distribution. So this is not computable without some a priori knowledge of this data distribution, which is what makes this problem difficult. And so then what we're going to do is layer on top of it an additional set of difficulties. So we're going to study the problem where you have multiple of these decision makers, and we have explicit competition, meaning that the loss for each player depends not only on their own actions, but the actions of others. And then in addition, their data distribution will depend on, again, their actions and the actions of others. And so several people have been formulating this problem, including Georgios, and then there's and his collaborators, and there's a group at UC Boulder who's also been working on the space. And I'll give credit to Adian and Evan, who are my students, who came up with this problem as a course project. And Adian's here if you would like to talk to him. He's sitting in the back. And so they came up with this idea to look at this problem. And so we've been working on it over the last year or so. And so again, I'll come back to this silly little example. So we have our rideshare set up. And so let's say Uber is this main guy here who's trying to make a prediction of demand. But now we have Lyft coming into play, and they're also showing drivers information and passengers information. And these guys are sort of comparing, where can they make the most money or which is going to be the cheaper ride. And so as a result, the data distribution of whatever learning problem, in this case, let's say predicting demand, is going to be a function of both platforms' actions. So we want to capture that. So what I'll do in the rest of the talk is describe two sort of settings. So one is the naive setting. So that's where players just say, okay, this is too difficult to deal with. So I'm going to kind of ignore that implicit partial gradient component or the explicit sort of competition that's showing up here. And we're going to do repeated retraining. And so for that case, we're going to come up with relevant equilibrium concepts, including existence and uniqueness, and then algorithms to compute those equilibrium concepts. Then we'll switch gear to where players have some level of, they're not as myopic. And so they come up with a way to estimate the effect of this decision dependence in the data distribution. And again, we'll do the same sort of setup, say when equilibria exist, when they're unique, and come up with algorithms to find those equilibria. And then I'll conclude with some little toy, so what we call semisynthetic experiments in this space. So I'll use some real data to illustrate sort of the interaction or the sort of compare these different equilibrium concepts. Okay, let's start with a naive case. And let's suppose players are going to do repeated retraining in a naive way. Okay, so what is repeated retraining? And what is sort of the natural solution concept that it converges to? So we'll start with a solution concept so we can think about the single player setting. And so I think this initially was defined in the paper by Perdomo et al. They call this solution here. So there's just one player and they want to solve this risk minimization problem, let's say. And so if they ignore the decision dependence, then we can define what's called a performably stable point. So you kind of fix your distribution at this XS, and then the solution of this arg minimization problem should also be XS, and that's a performably stable point. So we can extend this to the multiplayer setting. And the natural way to do that is define an auxiliary game. And so this game is a game just in the explicit dependence in the loss on, with respect to xi and x minus I, but it's induced by this y variable here. So this joint, so y here is an element of the joint action space. And so that shows up in the decision dependent distribution. So given that auxiliary game, we can define a performably stable equilibrium. And I put equilibrium in quotes here on purpose because it's not an equilibrium sort of in a game theoretic sense, but more in the sense of it arises as a result of the repeated retraining that I'll show on the next slide. And so essentially we want it to be a point that is for each player is an argmin of this optimization problem where sort of importantly we have XS in the decision dependent distribution here and then X minus IS in the loss. Okay. Oh. Okay, yeah, I guess before getting into the definition of this repeated retraining, we're going to set up some assumptions that we'll need throughout. So we have sort of the sort of typical things here for our joint action space. It's going to be convex, compact. These conditions are going to be needed to get existence. And then we're going to assume that our this auxiliary game here. So for any y, any joint action y, the auxiliary game induced by that y is alpha strongly monotone. And so I put the definition here of strong monotonicity for a game just as a way to remind folks, but essentially it means that for some game defined by these cost functions f here, if we look at the vector of individual gradients, we want that guy to be, that mapping to be a strongly monotone mapping, which just means this inequality here holds. And so what does it mean for this game to be strongly monotone? Well, one way to start to think about what this means and how restrictive it is, if we think about the case of separable losses, so let's suppose this loss here doesn't depend on x minus I. So we still have the competition through this decision dependent distribution. In that case, then all this assumption 2 means is that the losses are going to be strongly convex in the choice variable of the agent. So that's sort of what this boils down to if we remove that explicit dependence on x minus I. Okay, so then we're also going to need some regularity conditions on our losses. So they need to be sufficiently smooth. And we need some smoothness condition on the partial gradient of the loss with respect to xi. We also need some growth conditions on our or regularity conditions on our decision dependent distribution. So this is the Wasserstein 1 distance here between the two distributions induced by x and y, and we need that to have satisfy this inequality. Okay, so these are the sort of assumptions we're going to make, and then what we're going to do is define this quantity rho down here, which just has these sort of regularity constants showing up here in the numerator, and then the strong monotonicity parameter in the denominator. So this guy is going to be fundamentally important for ensuring that our algorithms actually converge and that we have existence of equilibria. Okay, so
May I ask for clarification?
Yep.
Initially, I thought that the model has only the x and xi. You remind again, because it's the first time that I saw the model. What is the G? I mean, what is the game? Where the game is playing the role? What is the role of the game?
let me just go back here. So each player is choosing, so player I is choosing xi.
Okay.
And their distribution, the data distribution depends on xi and the decisions of all the other players, x minus I. And similarly, their loss also depends on xi and x minus I.
Okay, and then where is the game and operator, the monotone operator that you refer?
Oh, so maybe I don't know what you're asking. Yeah, so you're asking. Yeah, what are you asking exactly?
What is that G of Y?
Oh, it's this. It's the auxiliary game induced by Y. So Y shows up down here, and then we have a game still in terms of the explicit dependence in the loss function.
Oh, okay.
So there's still a game, even if we fix Y here, there's still a game between the players here.
Okay.
What is Y exactly? Is it something?
Any joint action in the joint action space of all the players. So we can define a game for any Y. We can define this auxiliary game. Does this make sense? This is fixed, but we still have the dependence on xi and x minus I. So this is because, maybe it'll make sense once I define repeated retraining. So what repeated retraining is in a single player case is you also sort of fix the distribution at the previous action, xt. And then you just optimize with respect to the explicit dependence in the loss function. And for the game case, we'll do the same thing. We're going to define this induced game by the previous action. And so that's xt here in the data distribution. And then we still have a game between the players in terms of xi. And so because we're defining Nash here, this is y minus I. So we want to, for the repeated retraining case and the multiplayer case, we're going to compute a Nash equilibrium of the game induced by the previous action xt. This makes sense? Okay. All right. So then when we have, now that we have this repeated retraining process, we can figure out when performatively stable points exist and then show when repeated retraining converges simply with a sort of fixed point argument. And so in order to make sure that this thing is a contraction, this process that we're repeating on, we need rho here to be less than 1. So then simultaneously, this sort of gives us existence and in fact uniqueness because of the nice conditions we've assumed on our cost functions and things, as well as convergence of this process. So yeah, this is when rho is less than 1 is the interesting regime here because in terms of the problem parameters, because this gives us the setting in which we have an equilibrium that exists. Another interesting thing to point out, if we look at the separable case, so again, this just means that the loss function in this, let's go back to this. So in this case here, if in the separable case, there's no dependence anymore, explicit dependence in the loss function on the actions of others. So then it's just for each player, it's simply an optimization problem. And so in that case, the only competition is occurring from the previous iteration, so in the decision dependent distribution. And so in that setting, we end up getting the interesting regime being the setting where rho squared can be less than 1. And that gives us an improved rate in terms of square root rho. And I guess the important thing to mention here is that it matches the single player setting. So in the single player setting, there's no competition at all. And so if you are actually to write down convergence guarantees and existence guarantees for these performatively stable points, then you'd find that the parameter that shows up here is in fact square root rho.
To be clear, under your assumptions, this Nash operator is a single equilibrium, like at the top
Yeah.
is a single equilibrium, right?
Yeah.
Yeah, in performative prediction, usually there is performative stability and performative optimality.
Yeah.
Do you have a notion of performative optimality?
That'll be the same. I'm getting to that after I finish this repeated stuff. We'll talk about Nash.
Okay.
Nash is the sort of natural generalization of performative optimality.
Okay.
Well, there's two sort of generalizations. If you care about, the social optimum or something like that, so completely competitive or cooperative, so no competition, everybody's like optimizing the joint or the sum of losses, then maybe the natural generalization would be the social optimum. But if it's competitive, the natural generalization is a Nash equilibrium.
Which is the performatively stable equilibrium too?
No,
No,
this is a different Nash equilibrium.
Exactly, yeah. Okay.
Yeah.
I'm sorry, probably you explained this, but I missed it. How exactly do you calculate the equilibrium of G of xt? You need the Nash of G of xt, right?
Of G of xt. Sorry, I
Yeah.
didn't hear what you said.
How do you calculate that?
I'll talk about that in just a second.
Okay.
Just to understand some, the way that it is written, the operator is trying to compute a generalized Nash equilibrium in a concave game. Yes, or
Yeah.
Okay.
Here, let me talk about how we can actually compute this. So one way to compute this guy, it's not even, we're not even any, so as we run this algorithm, we're not going to compute the Nash equilibrium of, a bunch of iterates. We're not going to compute the Nash at each instance induced by xt. Instead, what we're going to do is run this repeated stochastic gradient play, and this will converge to the performatively stable point. So in each step, players just do a myopic update following their individual gradient. And what's important here is that the gradient they're going to be following is just part of the actual gradient. So the actual gradient of the loss has this extra term due to the decision dependence in the distribution. And so instead, what they're going to do is just use the thing that we can compute stochastically without knowledge of d of x, which is just samples of this first term. So if we run this process, we can show that this converges to the performatively stable point. And the way that we're going to do that is first get a one-step contraction. So this is standard in optimization, and strong monotonicity enables us to sort of prove these results as a fairly natural generalization of what we know in standard optimization. And so the only thing we need here, in addition to the assumptions that I listed before, is we need some variance bound on our gradient estimate. So this G here, these sort of stochastic samples of this explicit partial gradient, these guys are going to be the estimates that for the individual gradients that each player is going to follow. And so we need some variance bound on those estimators. And we need the expected value of this guy G to be L Lipschitz. And then with that condition, in the regime where rho is less than 1, so this gives us existence. If we choose our step size appropriately, then we can get this one-step contraction. Once you have a one-step contraction, you can do all kinds of different algorithms to converge to the equilibrium of this process, which is the performatively stable point. One such algorithm is to just decay the step size in half over a bunch of epochs. So the way it works, we're going to divide our time up into capital K epochs, which I'll define here in a second. And we're going to run this repeated stochastic gradient play algorithm for capital T naught steps. So this is proportional, inversely proportional to eta naught here. And then in the next iteration, we're going to take where we ended up as the initial condition for the next epoch. And we're going to cut the step size in half, again, inversely proportional to eta 1 here. And if we keep repeating this process, we can show that after capital K epochs, which depends on our target accuracy epsilon here, so we'll set that at the beginning. After capital K epochs, we'll be within a epsilon neighborhood of the performatively stable point. And so we can get the following result that says, what is the total number of iterations that we'll take? So the iteration complexity. So that's basically the sum of these TKs for K equals 0 up to capital K. So that will have iteration complexity as given here. So essentially exactly what you would expect for any stochastic gradient method. We'll have the same kind of iteration complexity.
But what is the X star here? I mean,
The performatively stable point, the performatively stable equilibrium.
The initial.
What is the initial equilibrium?
I mean, the equilibrium that we were setting of the
Yeah,
operator.
yeah.
Sounds a little bit magic because we forget at all the second, the implicit gradient. What we did with the implicit gradient.
I will talk about how we can use the implicit gradient, but this is saying which point do we converge to if we ignore the implicit gradient. So the definition of performably stable equilibrium has to do with ignoring that component completely.
Okay.
Yeah. So it's not it's called an equilibrium, but it's not in any game theoretic sense. It's in the sense of that repeated Nash process. Okay. So now if players are no longer naive, so they're going to now care about that explicit or the implicit partial gradient. So we want to compute Nash equilibrium now. So the difference between the performably stable point and the Nash equilibrium is shown here. So we actually now optimize over the decision dependence in this distribution, whereas before we were not doing that, right? We were just putting excess into that distribution. So this is our definition of Nash. It's pretty should be fairly standard because we're looking at the decision where in our optimization problem does xi show up in all places. Okay, so again, we're going to ask the same questions. When do equilibria exist? When do these particular type of equilibria exist? And then what algorithms are going to converge to them? Okay, so we'll again use this sort of classical or this strong monotonicity property. And the reason is that we know from Rosen's classical paper from 65 that if you have a strongly monotone game, then you get existence and uniqueness of the equilibrium, so the Nash equilibrium. So again, I just to remind the definition of strong monotonicity. And so how we're going to use this to get existence for this decision-dependent game is as follows. So first, we already have the assumption that the game induced by any y is alpha strongly monotone. And so that relates to the strong monotonicity of this explicit component of the gradient of the loss function. So in particular, if I just write out what it means to be alpha strongly monotone for this game, it's literally that this mapping g subscript yx, which has all of these, for each I, it has all of these components here. That mapping needs to be strongly monotone in x. So for fixed y, this guy needs to be strongly monotone in x. That was the assumption we already made. So now we need some assumption on this second piece to ensure that we have strong monotonicity of the overall game. And so to get that, we're going to do something similar to what we did with this first piece. So first of all, we're going to define this hxy vector. Sorry, I swapped the role of x and y here. So y is the, so in this operator, so y is the explicit dependence in the loss function on the actions of the player. So again, y is a joint action profile. And the subscript x is the dependence in the data distribution here. So down here, we have y and then x in the data distribution. And so what we can show is that in the regime where rho is less than a half, same rho from before, as long as this mapping here, so from x to h subscript x, y, if that guy is monotone, doesn't need to be strongly monotone or strictly monotone, or sorry, yeah, doesn't need to be strongly monotone, just monotone for any fixed y, then the game will be strongly monotone and the parameter will be 1 minus 2 rho alpha. That's why we need rho to be less than a half for this game to have a Nash equilibrium and it be unique. Okay. So I'll just give an example. If people are interested, I can show how we actually make this argument, but in lieu of that, what I'll do is just give an example of how this happens again in this example of Uber versus Lyft. So let's say that these rideshare companies now, they want to maximize their revenue. So this first term is so we're doing loss minimization here. So negative the revenue is going to be their loss. The first term is the revenue here, and then we have some regularization on the vector x here. X is going to be the price, and z is going to be the demand. And if we have this set up where z follows a location scale distribution, so here really we're just talking about the location parameter being affected by x. So we have some base distribution defined by this random variable zeta here. And then we have the price elasticities due to competition, due to competition and due to your own sort of performative effects, if you will. Then we compute these maps H for each player, H, X, Y. It's pretty simple. We just take the gradient of L with respect to Z, and then the gradient of Z with respect to XI, which is where the AI here comes up. Then this thing is just a constant mapping. So that doesn't even depend on X at all. So it's trivially monotone. So there's lots of examples like this. We give several other ones in the paper, but this is sort of a simple trivial one that shows when we satisfy the assumptions that lead to existence and uniqueness of the equilibrium. All right, so we have existence and uniqueness, and now we want to talk about algorithms.
Yeah. Okay. Second example that makes well-defined the definition of H. Do you have any characterization of what should happen to the distribution? Somehow, how I can understand?
Yeah, so in the separable case, when your loss doesn't explicitly depend on the competition. So if we just have expected value of the loss for Li, Xi, Zi, then this literally boils down to what's called a mixture dominance condition on the distribution. So it satisfies some convexity condition in itself. That's also known in the single player case. Yeah. Okay, so we're going to talk about two algorithms. So the first is kind of natural. If you don't have access to this data distribution, but you still want to account for that explicit partial gradient, then what we'll do is we'll look at derivative-free methods, and I'll show when those converge. In this case, where we have a monotone, strongly monotone game, and then we'll look at this setup that's motivated by adaptive control. So in particular, players will have a parametric description of this decision-dependent distribution and adaptively estimate that while simultaneously optimizing their individual losses. Okay, so for the bandit feedback setting, I'll just talk about this in the context of general strongly monotone games, because we actually have improved the rate for those, the known rate for those games. So the setup is as follows. We have a strongly monotone game defined on our convex compact joint action space here. And players are going to do this single point Flaxman style gradient estimate. And so what that means is every player perturbs their action using some query radius and a unit vector sampled from a vector sampled from the unit sphere. So if they do this, then it turns out, okay, so in the decision dependent setting, this is what this looks like. So we have our loss function again with these queries, and then our distribution is also going to be perturbed. So what it turns out is that if you take the expected value of this guy, it's an unbiased estimator of what's called the smooth cost. And then we can simply bound or make some arguments about the relationship between the smooth cost and the original cost of the game. And that leads to the results that we have, and I'll show that in a second. So once players have this gradient estimate, they're just going to do projected individual gradient descent. Okay, so the known convergence rates from 2018 had square dependence on the dimension, and then epsilon minus 3 in terms of the target accuracy. These were shown by Bravo et al. They conjectured that the rate should be what we have down here. So this is also the optimal rate in the single player setting for these single point gradient estimates that I've shown. That if you have multiple point gradient estimates, you can do a little better than this. You can get a square root d factor instead of the d squared dependence. So we're able to get this rate for general strongly monotone games. And so then that, of course, applies to the decision dependent setting that I was just showing. So I also want to mention that at the same time that we proved this rate, T&E and some of his collaborators, so T&E is a grad student here, got the same rate using a different method. So it's kind of cool, but we were able to show this for this particular 1-point gradient estimate. They have a similar 1-point gradient estimate, but they use a concordant barrier function to get the same kind of rate. Okay, so how do we do this? We actually have the proof is really short. So the intuition is as follows. We're just going to view everything in terms of structural stability of perturbed games. So we define our Nash equilibrium of the original game was going to be this X star here. So the original game in terms of F on X. Oh, one important point that I didn't mention here is that players, when they're doing their projection, they're doing it on a retracted set. So this is their query radius that shows up here. And you want to retract that set to ensure that when you are evaluating your loss function, you're doing it inside the constraint set X. So that's important.
So can I also, so each player completes a zero order gradient with respect to their own strategies?
Yeah.
So what is this delta something added to the second coordinate? Like,
so the other player is also doing that. So this is what they're querying the environment with as well. So all of them perturb their actions, send it to some oracle. Oracle sends back all of the losses.
that's
Okay. So yeah, so we're gonna yeah.
The rate of convergence that you get in terms of the play actions or in terms of the unperturbed actions?
In terms of XT, so this is not like XT plus delta, if that's what you're asking.
Yeah, that's what I'm asking because actually, I mean, the player actually plays, what the actual play is X plus delta, right?
Yeah.
Okay, so this is the guarantee for XT, not
For XT, yeah.
Okay.
So like if they run it for, I'll give, so let's say they run it for capital T iterations, then the last iterate that's produced by the algorithm, that will be the Nash equilibrium, or satisfy this guarantee. Not the Nash.
But wait, I'm confused. The players are playing the XT plus delta or the XT, because you say
They're querying the environment with X plus delta V.
okay, but the rate is about XT.
I mean, they're choosing those deltas and V's, right? So the ultimate goal is to find this Nash equilibrium. If they stop after some time, then they'll have this, we'll have this guarantee.
The question is that the distance between XT and XT plus delta is obviously delta. So the question is whether the actually played strategy differ by delta from the sequence for which you're providing the rate. If the rate is still the squared.
Yeah, I'm not sure, but I suspect
That was the question.
I suspect that's probably pretty easy to handle because the way we do this is, let me just show you. So we end up just splitting up the XT X star here into these different terms. And the second term, which I'll describe what it is in a minute, is just delta times something. And then we choose delta to make sure that's small. So if we also had a delta times, V or whatever, then that, I don't think that would matter at all. We just have like a plus one in times inside this term.
So if you choose delta to be something in order to cover some properties, then it doesn't seem that you can choose delta in order to cover also the.
So if you want to get the rate for XT plus delta V, I think we can get exactly the same rate for that result.
Okay.
And then we can also get the rate if we just did
Okay.
but not both simultaneously for the same delta. Maybe if you did some min or whatever, like choose delta to be the best of both cases. That would work.
Okay.
Okay, so yeah, I don't know how much time I have left in this, but I should pay attention to that. So yeah, the way we do this is that it's kind of a trivial little thing here. Defining the original Nash equilibrium, the Nash equilibrium for the original game on the set that we care about. Then we define Nash of these auxiliary games. So one is of the smooth losses on the retracted set. And then one is of the original losses also on the retracted set. So then using a triangle inequality, we can bound this first term because there's we can exploit some structural stability property of the viewing. This guy is just a perturbation of the original game. And we can bound that in terms of delta. The same thing. Turns out that you can relate the normal cone for these different sets and leverage that property to just bound that second term. I can show details if people are interested, but otherwise we'll kind of move on. Okay, so we want to talk about now the second set of algorithms. Let me just check the time. Okay, like a few minutes. So the second algorithm class is going to try to exploit some knowledge of the underlying distribution. And so again, we're going to appeal to this location scale family where it is the location parameter that is dependent on X. And so here, players are going to adaptively form estimates of these matrices A that affect their decision-dependent distribution. And then the way that they do that is injecting noise such that the online least squares problem actually converges. So they're going to form an online least squares problem to estimate those A. And so the algorithm looks a lot like adaptive control, because that's basically what it is, except it's in a multiplayer case. So players inject noise and they query the environment. And so they're querying the environment twice. So one at xt and then one at xt plus this injected noise. If we don't want to deal with multiple queries, I mean, this is only to deal with like not assuming that the base distribution zeta is zero mean. So it's just a technical thing here. Otherwise, they could recenter everything at each step as well. And so they do an estimation. This is just one step of least squares here, online least squares. And then they simultaneously do a gradient step using the estimated implicit partial gradient in addition to the original stochastic explicit partial gradient. So this actually converges at the same rate as if they already knew those matrices A. And so I'll just kind of show, this is a synthetic simulation example showing that the rate matches the stochastic gradient play, and then the derivative-free method here converges, but does so at a worse rate. So the key idea here is similar to what we see in adaptive control, is that we want our estimation problem to be persistently exciting, so we inject noise appropriately to achieve that. So I think an interesting open direction is to think about estimating that implicit partial gradient using techniques from adaptive control. So for example, it's known there that certain classes of functions are already have these persistence of excitation properties, like radial basis functions, for example. And so an interesting direction is to try to have more general descriptions of our decision-dependent distribution that already have the nice properties that ensure that we can estimate them. Okay, so I'm going to conclude here in the next few minutes by talking about this rideshare kind of toy problem, but using real data. So this is what people call semi-synthetic simulations. And the goal will be to just kind of expose some interesting things that we observed empirically that I think lead to open questions. Okay, so each player again is going to try to maximize their revenue or minimize the negative of their revenue here with some regularization term. We have some base demand. There's going to be different effects. You'll have your own performative effects. And so this is just representing, it will represent some negative price elasticity. And then we'll have some positive price elasticity due to the competition. So your competition raises their price, it's going to increase the demand for your service. So there's a nice little data set on Kaggle here from Boston that has both Uber and Lyft data in it. So it's really hard actually to find these nice data sets where people have actually taken multiple actions and then users have responded, much less have this competition. So this data set's not huge, but it serves its purpose for what we're doing. And so what we do is we take the data, which has rides at different prices with different surge mechanisms from different locations for each of the different services in Boston over a 14-day period. And so we bin the rides into $5 increments, so 0 to 5, 5 to 10, and so on. And then for each bin, we we have an empirical distribution. So we just sample from that bin, and then we're going to treat the decision as the surge price for each bin. So how much do you add extra on top of the cost? And then we estimate these performative effects from the data. Okay, so the first is just a simple little observation that if players ignore the competition, so ignore the performative effects due to competition, if we compute the resulting equilibrium of the learning process that arises from that, them being myopic, in the case where either Lyft's myopic individually, Uber's myopic individually, or both are myopic, they perform better, they have more revenue under the Nash equilibrium. So this is suggesting that modeling performative effects is a positive thing for players to be doing. The second thing I think is even maybe more interesting and suggestive of directions to go. So if we compute a sort of price of anarchy, so we have a unique equilibrium here for both the case of performatively stable equilibrium as well as the Nash equilibrium, and we can compare to the social. So I'm talking about the negative of the losses, negative of the sum of the losses for the players, and then the social welfare being the negative of the sum of the losses for the players at the socially optimal equilibrium. So we're going to just use this as a metric. So if you look at a $5 to $10 price bin, so the price of anarchy for the performatively stable point is pretty close to the Nash equilibrium. And so we might care about this because this performatively stable point requires less assumptions to compute. It's pretty easy to implement naively without having any information about the decision-dependent distribution. And so it's interesting that in terms of social welfare, these are almost equivalent. So one thing, though, to point out is that if you look at the market share in terms of revenue for the Nash equilibrium, it's more reflective of what the social optimum is, whereas the performatively stable point has this, some of the market share gets shifted over to from Lyft to Uber. So while they have roughly the same price of anarchy, at the same time, the market share distribution is wildly different. So that's an interesting observation. And then in the $15 price bin, we kind of have a different sort of story. So the performatively stable point is much, the price of anarchy is much lower, so worse than the Nash equilibrium. And you don't have quite as big of a disparity between, there's still some in terms of market share, but not quite as big. So this suggests that an interesting direction would be to have a better analytical characterization of quantities like this, and then also to think about, okay, well, if points like the performatively stable equilibrium are better in terms of social welfare, or vice versa, how do you incentivize players to go after those versus the other equilibrium concept? Yeah.
I'm not really aware of data science, so how did you run these experiments? Are data? I'm trying to understand, but how did you learn this $10 or $15 price?
Oh, so the data actually has the price of the rides.
And they are open, you mean?
Yeah.
Okay.
It's on, so Kaggle is one of those competition sites for data science, and they post a lot of free data. So if you're interested in getting data, that's a good place to go. Yeah. So they put it up there. So yeah, otherwise this is really hard to get data like this type. So yeah, for sure.
How did you compute the externalities of one to the other, the A matrices in your notation? How did you estimate those from the data? The A matrices.
Yeah. So, Annie, do you remember how you guys did this? How we estimated the A matrices from the data? You and Evan came up with some scheme for that.
Oh, like the actual A matrices.
Yeah.
Right. I feel like we use some kind of heuristic about how the demand should be affected by changes in price, and it was definitely like very ad hoc and kind of synthetic in a way, but it definitely should align with if the other person's price decreases, then your demand should go down, and if the other person's price increases, then your demand should go up. And then the amount that change should happen was like if the other person's price increases by like a certain percent, say like 10%, maybe your demand should go down by like 5% or something. So if you just use like some heuristic numbers and put them in there, then you can just backtrack and come up with some equations.
So, but the result was a symmetry between Lyft and Uber, right? So
there was more rides for I think Lyft in the data set than Uber.
So yeah, so the cause of this asymmetry was, I mean, in this formulation, the only asymmetry I see would be, I don't know, the ZIs are different for Lyft and Uber. I mean,
yeah. So
so you use the same matrices but different distribution for ZI.
they have different matrices for each player. So there's different A matrices for each player.
Okay, so you did estimate that from the data set.
Yeah, in some way. So there's a heuristic for like how, like what the relative proportion I guess it should go up or down based on the increase that one player makes versus the other, but then you actually use the data to get the actual values, right?
Exactly, yeah, that's exactly.
I think we described it in a paper, but I don't. Sorry.
Is that you're using the adaptive control root estimation?
Sorry.
Is that what you are using the adaptive control gradient, like the adaptive control update root estimate data, or?
Sorry, I don't think I understand what you're asking. So in the adaptive control algorithm, players are estimating these things. So we, in terms of estimating those for the simulation, that's a different thing. So we estimated those from the data using a heuristic.
Yeah.
And then we simulate the environment using those estimated matrices, and players are estimating using this.
Oh,
So that's what these things are like, semi-synthetic simulations, in the sense that like you're simulating the performative effects based on some estimation of those parameters from the data. But then players are still trying to learn those things.
Sorry, because I'm confused too about that. Initially, I thought that we're trying to estimate alpha with a least square approach.
The players are. But there's a difference between like the Oracle simulator that's running underneath. So we have a simulation environment that simulates the environment. And to set that simulation up, we estimated we as the, like us, as the scientists, estimated those matrices from the data. And then we run a simulation on top of those where the players, Lyft and Uber, are estimating the effects of A. So there's like different kinds of estimation there.
It couldn't be the case that we have a single agent to extend. I mean, if you run it, I'm a bit confused on that. If I say that I am the scientist in a single agent environment and I'm trying to estimate with that.
No. That's just to set up the simulator. So like, just like you set up a robotic simulator or something like that, you need to pick parameters to run the simulator. So we pick parameters to run the simulator, and the way we do that is based on heuristics from the data. Then we run the Lyft and Uber on top of that. And so when that's basically to create the oracle, right? So when Lyft and Uber sample from the loss function oracle, that's based on our simulator that we set up using the data.
So you're trying to set up the ground truth actually in the first step.
Yeah.
Okay.
This is again why it's called semi-synthetic, because it's not
I see.
real. Yes.
Yeah, elaborate, because this is a broader challenge, it seems, with semi-synthetic, in that you're using data to analyze a decision problem where the data depends on decisions.
Yeah.
And so there's a chicken and egg.
I completely agree. And so, moving forward, we're doing some actual experiments with, decision makers, individual humans, for example, where we can actually deal with that problem. Another way to deal with it is to break the data up. So you're only estimating from some chunk of the data, and then you're simulating on the rest, like we do in machine learning. But yeah, I completely agree. This is a huge problem in this space. Yeah. It is in general in control too, right? So.
When you talk about social welfare, you're talking about like the revenue, like to the social optimal, or like the revenue maximizing strategies for Lyft and Uber, right? We're not talking about like good consumers or the. Yeah.
No model of those individuals. Yeah. That's a good point. Okay, I think. Oh yeah, we're out of time. So, that was basically it. I just wanted to end with one thing here. So some of the open questions that I think here are, there's like huge number of open questions beyond this semi-synthetic thing, which is also a big issue in this area. But, so we talked a lot about, at the beginning I motivated this strategic behavior, but we really were abstracting out that strategic behavior in terms of an ensemble or a population level distribution. And so really, there's some interesting questions related to building in behavioral models or more specific human decision-making models that capture, things like comparing to reference points or risk aversion, et cetera. In addition, we talked about one population of users. It's also of interest to think about multiple populations of users and how the market share splits up amongst those users. And related to that is incorporating sort of economic constraints like individual rationality for those users. And so, for example, users might decide if they're comparing to an outside option to just not participate. And so then you'll have this sort of attrition in the underlying population. And so that's an interesting effect to sort of account for. And then finally, in machine learning, we don't just care about optimization performance, we care about things like generalization error. And so that's, so there's some open questions around actually defining what that means when you have decision dependence. So there's a little bit of work on reinforcement learning that tries to do this. But I think that's an interesting direction to go, as well as more formally characterizing those efficiency bounds, like things like price of anarchy, et cetera. So I'll just conclude with that. And if anybody's interested in working on any of these things, I'm happy to collaborate with anyone. So you can certainly reach out. So that's it.
Questions?
Your setup feels a lot like a multi-population mean field game. And like where, for instance, in that example you gave, your like the demands felt a lot like the state space, and you have like, and what you're solving for really feels like a mean field Nash equilibrium. Like, are you aware of any connections? Like similar results hold also in that literature?
Yeah, so it's not quite, the setup I have isn't quite a mean field game in the sense that you're like the decision maker is just still optimizing its loss, but it just has some decision dependence in its distribution. So it's more like a degenerate reinforcement learning problem where there's a static underlying distribution. However, a natural next step would be to think about the population, so that decision dependent distribution actually changing in time following some mean field dynamics. So let's say users in that population are actually competing with each other and they have homogeneous preferences, et cetera, and maybe they have their own loss. And so then you would have this evolution of d of x dependent on time as they're learning in some mean field sense.
So you're saying that's like the difference between, I guess, an exogenous versus an endogenous change in the model, or?
Here, both are talking about endogenous changes in the model. Exogenous would be like some external, additional external input.
Okay.
Endogenous from the perspective of the
Yeah,
decision dependent learner. Exogenous from the perspective of the population.
Okay. I guess I don't really see the difference. I'm sorry. I'll come
So
back
there's
later.
two different decision makers, right, in that sense. So you can think about the decision dependent learner who's optimizing the loss given this decision dependent distribution.
Yeah.
And then you can also think about that decision dependent distribution as a population of agents optimizing some loss function in a mean field sense, which we haven't done here, but that's an interesting direction. So
Okay.
there, X would be an exogenous input to that population. But from the point of view of the decision dependent learner, it's an endogenous effect on the population.
Okay, I see.
Any other questions?
Yeah, thanks for the talk. Very interesting. So just curious about made several assumptions about the convexity of games. How plausible are they going to be in the reality? For example, your experiments, are these like very satisfied or just curious about
I think so for the simple model that we set up with this revenue maximization. And then also for like, people look at strategic classification where you have some logistic loss with a regularization term to improve generalization performance. Those all satisfy these conditions. But it is a fair assumption that you could have, if you had some more complicated like neural network kind of architecture or something that's part of this, loss minimization, then that totally would be non-convex. So yeah, it's definitely an interesting direction to try to relax those.
Just following up on that question, do you know if it's possible to remove the regularizer and get like something that works under monotonicity but not strong monotonicity?
That's a natural next step. I haven't thought about it, but there's tons of papers looking at optimization in games for when you relax that. So I think completely would be worth looking at in this context too.
So I want to go back to the question of Jeff. What I'm trying to understand a little bit is the applicability of the model, because we want to see what the players will play from some data, but at the end of the day, how the data creates this alpha. Would you like to make a comment about that? Because I'm trying to understand.
I think the only real way to test those kinds of things is to have actual experiments, working with companies or setting up experiments yourself where you actually have, like, say, human decision makers or something like that that are reacting to your decision. Maybe, for example, the previous talk was looking at, you have kind of estimating ensemble behavior in these game theoretic contexts in an experimental way. So perhaps, engaging with people like that who are, like Drew, who are already doing these kinds of experiments. That, I mean, you have to, I think that's the ultimate answer to the question, right? You need to do real experiments. Because these semi-synthetic things, they're wrought with problems of this sort. Yeah, and I'm not going to defend that in any way because I completely agree. Yeah.
Okay, thank you.
Any other questions? I have a question actually. First of all, thank you for your talk. Very, very exciting. So, I'm like the CEO of maybe let's say Uber. So how do I use this paper? Like, how do I make more money? Like, is there any, yeah.
If it's true that you should model performative effects, then you should be thinking about how your competitor is making decisions too. And I'm sure they are, I'm sure Uber is already trying to think about that kind of thing. I wouldn't be surprised if they're not tracking their drivers and seeing like when they're on other apps and stuff like that. So yeah, it's some of these things are sort of simple stylized models and they're making much more complicated decisions. But I think if the underlying principle is true that you should be modeling the effects of your competitor, then that's just a suggestion for them to do so.
But does it also create like a level of like Kth rationality where like I have to take into account that my opponent like tries to like model my behavior where I'm also like trying to model their behavior. So is that like,
I think that's also interesting to think about. If you have conjectures, like let's say that it's not true that they have these location scale distribution, but you model it as that. And so then you have a conjecture essentially about what that behavior is. So you try to estimate that conjecture and maybe the other guy's doing the same. And so you could certainly have this nested kind of behavior. And actually my student Ben is working on this in the context of human machine interaction. So there is something called a consistent conjectural variations equilibrium, which actually predates Nash, that has this kind of natural nested conjecture and estimation concept. And so that's one of the things we're actually working on in terms of human machine interaction, not in this context, but it would certainly apply here too.
Great. Any last question? Okay. If not, let's thank Lily again.
Thanks for the interactive talk. It's fun when you have people